Welcome to Tales from the Periodic Table. I'm your host, Ron Hipschman, and today we're going to talk about the element Americium. What you see here is allegedly a very small button of actual Americium metal. I have not been able to verify this. However, a source I trust, Los Alamos National Lab, says this yellow powder is in fact americium oxalate, which will probably be heated to make americium oxide. Here we see Theodore Gray's beautiful periodic table. As I've mentioned in previous episodes, Theo has written one of my favorite books called The Elements, which I encourage you to pick up. Check out his fantastic website, periodictable.com. Americium is the 95th element in the periodic table. Its atomic number is 95 because that's how many protons are in its nucleus, and that is what distinguishes it as a unique element. Dmitri Mendeleev, often considered one of the fathers of the modern periodic table, was trying to make sense of how the elements related to each other. He was smart enough to know that he didn't know everything, and there was room for future discoveries. His table was originally published in 1869, and you can see he future-proofed his table by leaving spaces for as yet undiscovered elements. In our case, he left a space for americium after the also as yet undiscovered neptunium and plutonium. Like all the elements in this part of the periodic table, we don't have to go back in history very far for the discovery of americium, only back to the Manhattan Project during World War II. Americium was discovered by this group of physicists and chemists: Albert Ghiorso, Ralph James, Leon Morgan, and Glenn Seaborg. Seaborg received a Nobel Prize for his work. When the existence of americium was declassified in 1945 after World War II, Seaborg announced the discovery of the element in an unusual forum. Rather than at a stuffy scientific conference, he made an appearance as a guest scientist on a radio show called Quiz Kids. During that show, one of the kids asked if any new elements past plutonium had been discovered. Seaborg answered that yes, elements 95, americium, and 96, curium, were both found. As an aside, curium was actually discovered before americium. They used the new 60-inch cyclotron built by Ernest Lawrence at the UC Berkeley Radiation Lab, later called the Lawrence Radiation Lab, and even later the Lawrence Berkeley National Lab after the word radiation became too politically sensitive for Berkeley. In the accelerator, you start with plutonium-239. This was available from production for the Manhattan Project. The accelerator is used to produce a stream of neutrons. When these neutrons hit the plutonium-239, you get a new isotope, plutonium-240. That can then absorb another neutron and become plutonium-241. Plutonium-241, with a relatively short half-life of 14.33 years, then decays by beta, transforming into americium-241. Making americium like this with a cyclotron is a slow, expensive, and not very productive method. Most americium is derived from nuclear reactors, where you also have plutonium byproducts of the uranium fission process and lots of neutrons to spare. You only need to separate and purify spent nuclear fuel, and you can get as much as 100 grams of americium for every metric ton of fuel. Yes, you can probably guess where this element got its name, but even though it was discovered in the United States, maybe I'm being a bit too provincial. Let's include all the Americas, and from these two continents we get element 95 Americium. At first, the researchers referred to americium as pandemonium owing to the difficulties they encountered trying to isolate it from another new element with which it was closely associated, element 96, curium, or delirium as it was first called. But I digress. The name americium may also have been chosen because it's located below europium, element 63 in the periodic table. Europium was named after, I can tell you're getting the hang of this, Europe, of course, now called the European Union. Americium is a member of the actinide series of elements down at the bottom of the table. It's the seventh element of the actinide series. The elements of this series are chemically similar to the row above, the lanthanides. All the actinides and their isotopes are radioactive. Let's look at isotopes. Each element has many different forms. For each specific element, the number of protons in the nucleus is the same, 95 protons for americium. But there can be different numbers of neutrons in the nucleus. All these different forms are called isotopes. They're chemically identical to each other, but with slightly different masses. The number you see next to the chemical symbol is the total number of protons and neutrons in the nucleus. There are 19 known isotopes of americium, and as I mentioned in the previous slide, we've reached the portion of the periodic table where there are no stable isotopes. All the isotopes of americium are radioactive. We don't really find americium in nature. Only very trace amounts might be found in uranium minerals due to neutron capture and beta decay, but those amounts are negligible. The word isotope comes from the Greek, isos meaning same or equal, and topos meaning place. You've used a topographic map to find your place, I assume? All these various isotopes of americium occupy the same place in the periodic table. Of the isotopes of americium, these are the longest lived, the ones with half-lives over 1 hour. More on half-life in the next slide. The longest americium half-life is americium-243, with a half-life of only 7,350 years. That may seem long, but is actually very short compared to the 4.5 billion year age of the Earth or the 13.8 billion year age of the universe. That's why it's not found in nature. All americium has decayed away. It has to be manufactured. More on that later. I'll show you the americium decay series in a different way than I've done in the past. We're going to follow the bold path down the series since this represents the most likely path. In reality, this is the same as the neptunium decay series I've already covered in the past, since neptunium is a daughter product of americium decay. Through various alphas and beta decays, which are labeled along the path, we go from americium to neptunium to protactinium to uranium, thorium, radium, actinium, francium, astatine, bismuth, polonium, lead, another isotope of bismuth, and finally, stable non-radioactive thallium. To get the complete scoop on this series, see the episode about neptunium. What's a half-life? This graph shows an exponential decreasing curve. As an example, let's say we start with 1,024 atoms of any radioactive isotope. I chose 1,024 atoms because it's a power of 2, and we'll be doing a lot of divisions by 2. If we wait 1 half-life, 1/2 of your isotope will decay, and we'll have 512 atoms left. If we wait 1 more half-life, half of that half decays, leaving us with 1/4 of the original 1,024, or 256 atoms. Another half-life, half again as many, or 128 atoms, and so on. Just keep dividing by 2 every half-life. After 10 half-lives, we'll have about 1/1000th of our original amount. By the way, notice there's one remaining atom after 10 half-lives? If we waited one more half-life, our remaining atom would have a 50-50 chance of decaying in that time. Since we're on our 12th radioactive element, 13th if you include bismuth, I'd like to repeat how radioactivity is measured. There are 3 interesting facets of radioactivity we should pay attention to. First, we might want to know how many disintegrations per second a given source gives off. This is a measurement of its radioactivity, the rate particles are emitted. This is probably the simplest thing to measure. You can use a simple Geiger counter and just count the number of detections per second. But you need to take into account the size or area of the detector and its distance from the source, and multiply the measured counts per second as if your detector could completely surround the source to catch all the disintegrations in every direction. The international unit for this is the becquerel, named after Henri Becquerel, who discovered radioactivity. 1 becquerel equals 1 disintegration per second, so most sources are in the kilo, mega, or even gigabecquerel range. In the US, we also use an older unit, the curie, obviously named after our dynamic duo Marie and Pierre Curie. 1 curie is the amount of radiation given off by 1 gram of radium, discovered by them, get it? 1 curie is 37 billion disintegrations per second, or 3.7 times 10 to the 10th becquerels. Compared to the 1 curie per gram for radium, Americium, with its shorter half-life, emits 3.43 curies per gram. Radiation carries energy, and that energy is deposited in your body or into any object the radiation hits. The next unit measures how much energy is absorbed per kilogram. This is called the absorbed dose. In the metric system, energy is measured in joules. 1 joule is about the amount of energy used to lift an apple from the floor to a table. The international unit for absorbed dose is the Gray, named after Lewis Harold Gray, a physicist who worked on the effects of radiation on biological systems. A Gray is equivalent to 1 joule of energy absorbed per kilogram. This is quite a bit of radiation, so you'll usually see units of milli or micrograys or something like that. In the US, we have used a unit of the rad, or radiation absorbed dose, which is 1/100th as large as a Gray, but still a large amount of radiation. Lastly, we want to know how this absorbed energy will affect you, and that will depend on the type of radiation, alpha, beta, or gamma, which bodily organs are exposed, and how sensitive these body parts are to the specific kind of radiation. This is called the effective dose. The units here are the sievert, named after Rolf Maximilian Sievert, who was a medical physicist. He studied the biological effects of ionizing radiation. In the US, we also use the rem, which stands for Radiation Equivalent Man. The sievert is just 100 rem, and the rem is 1/100th sievert. These are human health-based units. They take the absorbed dose and adjust it as an indicator for the potential for long-term health effects, such as cancer, genetic damage, etc. The effective dose is used to set limits on exposure for radiation in the home and workplace. For instance, you are allowed to be exposed to 50 millisieverts, or 5 rem per year in the workplace. You normally absorb about 67 millirem every year from the environment around you. That's 1/75th the allowed annual dose. A dental X-ray exposes you to about zero point 0.5 millirem. A standard chest X-ray, front and side, exposes you to up to 10 millirem. And a chest CT scan gives you up to an 800 millirem dose. Although radiation exposure always carries some risk, with medical X-rays or CT scans, the benefits always outweigh the risk. I normally talk about the abundance of the elements on this slide, but because of the relatively short-lived radioactive nature of americium, at least compared to the age of the universe, there's not much to say here. There's really none to speak of in the universe, having all decayed away by now, and none in the sun. Likewise, none in meteorites, and not enough naturally in the Earth to talk about except the tiny amount made in natural uranium deposits by neutron absorption. It's absent in the oceans, and of course, thankfully, none in us. That was a lot of red X's. As we've seen, where you have plutonium, you usually also have americium. In the U.S., americium was first refined from the processing of plutonium at the Rocky Flats plant in Golden, Colorado. This facility was closed in 1989 because of safety concerns, but it had stopped producing americium 5 years earlier in 1984. The stockpile of americium lasted until 2004, after which we purchased it from Russia. Given its rarity, if you had a reason to buy americium, you'd need to buy it through the National Isotope Development Center. They support the Department of Energy in coordinating the production and distribution of a variety of isotopes used in industry, research, and medicine, including americium. They were extremely kind and provided information aiding in the production of this episode of Tales from the Periodic Table. My thanks to them for their help. Americium isn't the most costly element, but it ain't cheap either. All I could find online was a price range from around $1,500 per gram to $6,500 per gram. That's much less expensive than I'd expect, given you have to separate and refine it from spent nuclear fuel, so I'm dubious of these figures. If anyone knows better, please leave a more accurate value in the comments. Unfortunately, the NIDC, from the previous slide, is not allowed to reveal pricing except to licensed organizations capable of handling these types of dangerous materials. Quite understandable. Even though there's no natural americium on Earth to speak of, there's a good amount artificially produced in reactors. An estimate places the total amount of americium at around 87,100 kilograms. That was in 2003, the last reliable figure I could find, and that amount is estimated to be growing at 4,000 kilograms per year, which would put us at about 175,000 kilograms now in 2025, about double the 2003 amount. That 175 metric tons would be a cube about 234 centimeters, or 7.7 feet on a side, a little taller than an average human. Incidentally, this is way more than the critical mass for americium, which is around 25 kilograms. Our cube would cause a massive chain reaction. Americium has a density of 13.67 grams per cubic centimeter. It's a fairly dense element. As a reminder, the density of water is 1 gram per cubic centimeter, and here are a few more densities of some of my favorite other elements and compounds for comparison. You can see americium's density is even higher than lead at 11.34 grams per cubic centimeter. Here's a graph of the elements from highest density to lowest density. I have a set of blocks so you can feel density for yourself in my live talks. My set of blocks have a wide range of densities, with the densest at tungsten, to lead, to copper, to iron, to titanium, to aluminum, and magnesium. I also have plastic and wood blocks, but those are not technically elements. Again, americium's density is 13.67 grams per cubic centimeter, near the top of the chart, maybe the 15th densest element, very near the density of mercury, though americium doesn't seem to be on this chart. Americium has a melting temperature of only 1,176 degrees Celsius, 2,149 degrees Fahrenheit. That's the 40th highest melting point, about the middle of our chart, and only slightly above uranium. Americium boils at only 2,011 degrees Celsius, or 3,652 degrees Fahrenheit, giving it the 54th highest boiling point of all the elements, below average on this chart. That's only 835 degrees Celsius above its melting point, giving it a much smaller liquid temperature range than our previous two elements. Please refer to those videos. One of the subscribers to this channel, SillySad3198, thought it might be nice to see a graph of liquid temperature ranges from highest to lowest, so here it is. The widest liquid temperature range is of neptunium, with a 3,356 degrees Celsius liquid temperature range. As I mentioned, americium's liquid temperature range is smaller than average, with a 835 degrees Celsius range, the 60th largest liquid temperature range of the elements. The smallest liquid temperature range belongs to neon, which is liquid in only a 2.51 degrees Celsius range. Notice all the noble gases and hydrogen have very small liquid temperature ranges. If we compare the size of the americium atom to that of hydrogen, we'd see something like this, though I'm only estimating the atomic diameter using its covalent radius, since its atomic diameter hasn't been measured accurately yet. The americium atom is about 4 times the size of hydrogen. Here's its electronic structure. By the way, a picometer is a trillionth of a meter. Atoms are disconcertingly small. Looking at all the element atom sizes, here we see them sorted from largest, cesium at the top left, to smallest, helium at the bottom right. My estimated size of the americium atom places it in the upper region of the chart, around the size of many of the rare earth lanthanides, and specifically yttrium and lutetium, around the 17th largest atom. Here's the periodic table of the spectra. If you excite atoms, they give off specific colors of light. This is the spectrum of americium. It has a moderately simple spectrum with a smallish selection of colors spanning the spectrum from red to violet. Spectra of the elements uniquely identifies them to scientists as each element gives off its own unique set of colors. Spectroscopy is one of the most powerful tools of science. Okay, I know you're thinking, for crying out loud, americium is a transuranic element, even a transplutonic element. How could it possibly have everyday applications? Well, the photo may give you a clue. You probably have some americium in your home. I'm sure you have a smoke detector or two. Virtually all of us do, either for safety or it's the law. The most common type, an ionization smoke detector, is one that detects smoke when it blocks ions produced by a weak radioactive source. Here's the guts of the smoke detector, minus the battery and beeper. It's not a very complicated device. In the middle of that disc, which is normally covered by a metal cage in a working smoke detector, you can see a tiny button. Magnified, this tiny 1/8-inch diameter button contains a tiny piece of foil on which has been deposited a tiny amount of americium-241 oxide, which is then covered with a very thin layer of gold. The Americium decays by alpha particle emission into Neptunium-237, which I covered in a previous video. Let's look closer at what's happening inside the smoke detector. We'll start with that tiny Americium source, emitting alpha particles into the air above it. Some of these alpha particles will crash into air, nitrogen and oxygen molecules for the most part. When this happens, some of them will have their outer electrons knocked off, resulting in free electrons and the remaining positively charged molecules, called ions. We place a metal plate on one side of the chamber and charge it electrically. In this case, I'll charge it positively. On the other side of the chamber, I'll put another metal plate and charge it negatively. We all remember that opposites attract, so the negative ions will be attracted to the positive plate, and the positive ions attracted to the negative plate. In practice, since the radioactive source produces ions continuously, we really have a constant flow hitting both plates. If I put a current meter between the two plates, you'd be able to measure this admittedly small current. If smoke gets into the chamber, some of the ions will attach to the smoke or be blocked, and there will be a measurable decrease in the electrical current between the plates. This is when you set off that annoying beeper, which hopefully wakes you up and lets you know you might want to check things out or maybe evacuate. More likely, you'll be cooking and waving a towel at the smoke detector nearest your kitchen. If you're worried about the radiation coming from your ionization smoke detector, have no fears. The alpha particles are very short range. Watch as my Geiger counter approaches the source. It does not see many alphas beyond a few centimeters or about an inch away. Air stops alphas, and if you get close to an alpha source, your dead epidermis cells stop the alphas too. While not dangerous externally, you don't want alpha sources inside you where the particles can interact with live cells. Americium, when combined with beryllium, emits neutrons. Usually, americium oxide powder is combined with beryllium powder and pelletized. It's then sealed inside neutron transparent materials to prevent the release of any radioactive material. So, how does all this work? We start with radioactive Americium-241. Let's move it off to the side and add a beryllium nucleus. The americium undergoes alpha decay, and when these alpha particles then collide with beryllium-9 nuclei, the beryllium-9 nucleus absorbs the alpha particle, forming a carbon-13 nucleus, which is highly excited. This excited carbon-13 nucleus is unstable and quickly decays by emitting a neutron, becoming carbon-12. The americium-beryllium reaction also produces gamma rays due to the de-excitation of the carbon-12 nucleus, but we're interested mostly in the neutron. To survey what's underground, especially in oil and gas wells, a neutron source, like we saw a couple slides ago, is part of a suite of instruments which may also include a gamma ray source, something to measure conductivity, and maybe even an ultrasound instrument. These are all placed in a package which is then lowered into the well as data is taken. Each instrument gives the geologist a different clue to what surrounds the borehole. The neutron source and detector is useful for determining the porosity of the rock layers along with water and hydrocarbon content of the surrounding rock. In case you want to look into this further, this is called well logging. Neutron radiographs are similar to X-rays, but obviously neutrons are used instead of electromagnetic X-rays. X-rays are absorbed by dense substances like metals, whereas neutrons are absorbed by lighter atoms, especially hydrogen, and hence give you a completely different picture of what's inside an object. Compare these two radiographs. The top is produced by penetrating neutrons and the bottom by X-rays. Notice the X-rays completely miss the plastic film cartridge. Plastics are hydrocarbons and have lots of hydrogen atoms, so plastic items show up in neutron radiographs. You can even see the sprocketed 35mm film in the neutron radiograph, but only the thin metal take-up spool in the X-ray. The X-ray photo shows lots of the metal mechanisms: sprockets, film guide, rollers, shutter, winding mechanism, and more. The neutron radiograph shows weakly or not at all. You'd think this would be a great diagnostic tool for medicine, but unfortunately, neutron radiography is not typically used on living humans. It would deliver a higher dose of radiation than X-rays and does not easily penetrate our thick bodies. Neutron activation analysis is a powerful tool, allowing you to find out what elements are in a substance. When the neutrons hit and are absorbed, nuclei in the rock can transform from a stable isotope to a radioactive isotope. You can then measure the energies of the alpha, beta, and gammas given off by these radioactive nuclei, and the energies can tell you which elements and their quantities with good precision. If the half-lives of the radioactive isotopes are short enough, these half-lives can be measured too, adding to the identifying data. For instance, in the U.S., 1964 and older silver coins contained 51.8% silver 107 and 48.2 silver 109, both stable isotopes. After absorbing a neutron, you have radioactive silver 108 with a half-life of 2.42 minutes and silver 110 with a half-life of 24.6 seconds. Both decay by beta into mercury 108 and 110. You can measure the betas with a Geiger counter. Gamma rays are also given off and can be measured with a gamma ray spectrometer. Neutron activation analysis is very sensitive, measuring as small as parts per billion. Some additional advantages of neutron activation analysis are that you can identify many elements at once. It's non-destructive, and it doesn't require sample preparation. Neutron activation analysis is used in forensics, archaeology, environmental science, material science, and other areas. Heat can be generated by radioactive decay. This is a pellet of plutonium-238. The pellet is red hot because it's so radioactive. The alpha particle emission heats it to this temperature. This heat can be used to generate electricity in what's called a radioisotope thermoelectric generator, or RTG. NASA's version of this is called the Multi-Mission Radioisotope Thermoelectric Generator, or MMRTG. Americium-241 has been proposed as a substitute isotope instead of plutonium-238. Both emit alpha particles when they decay. Currently, plutonium is heavily used in deep space and planetary missions by NASA. The New Horizons spacecraft, which recently visited the planet Pluto, had one of these nuclear generators on board. You can't use solar panels that far out. The Sun, almost 4 billion miles distant, looks like a very bright star in Pluto's sky. There is not enough light energy to generate the needed electricity. New Horizons MMRTG supplied about 245 watts of power at launch. As the spacecraft continues on its mission, the plutonium decays, supplying exponentially less and less power until, in the late 2030s, the generated power won't be enough to heat or power the spacecraft. MMRTGs were also used in the Pioneer and Voyager spacecraft, which have now left the solar system and are now sailing through interstellar space. Here's a better photo of the plutonium-238 oxide pellets before they're encased. Using americium as a substitute has advantages and disadvantages over plutonium. The advantage is that it has a much longer half-life than plutonium-238, 432 years for americium compared to the 88 years for plutonium-238. That means your spacecraft mission could last 5 times as long. Unfortunately, because the half-life is 5 times longer, that implies it also generates only 1/5 the heat. So, watt for watt, you need 5 times the americium to generate the same power. Americium serves no known biological purpose, and you, hopefully, have none of this stuff inside you. If you do, you've been getting too intimate with your smoke detector. As usual, we'll end this talk with Mary Soon Lee's elemental haiku about americium. Alpha particles, dispatched in smoke detectors, to protect and serve. In the next program in this series, I'll examine the element curium. I hope you'll join me. I'm your host, Ron Hipschman. Thank you for watching this Tales from the Periodic Table program about the element americium. For more Tales from the Periodic Table, see this playlist on my YouTube channel. And, of course, I'm required by law to say this, smash that subscribe button.